Hello everyone, my name is Dylan Hossein and I'm currently a third year mechatronic systems engineering student. This video just goes over a recent electrical personal project of mine that I'm eager to share. I call this project my makeshift DC power supply. So basically the whole idea of this project is to convert an AC line voltage, which is essentially the sinusoidal voltage that comes out of every outlet in Canada, into as close to a perfect DC signal as I can. And by the way, the clip you see in the background is me trying to feed the AC line voltage from a power cord into a transformer. So before I actually get into the circuit, I first want to discuss the transformer that I use. So here on the left is the transformer that I used, and here on the right is the signal after the transformer. And so upon reading the peak-to-peak value of 74 volts, I was able to do a quick calculation to figure out that the winding ratio of this transformer should be about 4.6 to 1, meaning that it is, of course, a step-down transformer. And conventionally in rectifying circuits, the first thing that must happen is that the input signal has to go through a step-down transformer so that it's safe enough to operate in the later parts of the circuit. And the reason why the signal is not completely fitting in the screen is because the oscilloscope has a maximum voltage per division of 10 volts. So this is as best as it can get being viewed on the oscilloscope. So my initial approach to the project was to construct a simple 4-diode full-wave rectifying circuit with a capacitor filter, which as you can see right now is this half of my circuit. And this is the circuit diagram I made for it. There would be a load here, but that's for later explanation. But however, after learning about different electronic components from my electronic circuits course, I decided to incorporate a variable voltage regulator to make an even more ideal signal, which I'll get into more detail later. But for the purpose of keeping structure to the explanation in this video, I'll refer to the first half of the circuit on the left as the rectifying portion, and the second half of the circuit on the right as the regulator portion. And by the way, this is how the regulator looks like, or at least my illustration of it. Regarding the rectifying portion, the theory behind it is as follows. During the positive half cycle of the sine wave, these two diodes will be on. And the path that the current takes is as shown. So through this diode, across the load, back through this diode, and back to the source. However, during the negative half cycle of the sine wave, current is drawn toward the source, therefore these two diodes will be on. And the path that the current takes will be as follows. Back to the source. So, however, regardless of the polarity of the input line voltage, you'll notice that there will always be a positive voltage drop across both the load and filtering capacitor, which is what we want. And the purpose of the filtering capacitor here is to discharge whenever the input sine wave decreases in amplitude. So regarding the actual configuration of the rectifying portion of my circuit, this is how it's shown. And what you can see here is the 4 diodes that are actively rectifying the signal. This is the filtering capacitor, and this is the load resistor. So the values of these are a 6.8 microfarad capacitor and a 10 kilo ohm resistor. So as for why I chose those values, it's for not really much of a specific reason. I could have used a 0.5 millifarad capacitor instead of a 6.8 microfarad capacitor to even further reduce the ripple voltage and choose an even higher resistor than 10 kilo ohms. However, that's not the purpose of the project, to minimize the ripple voltage. Later on in the project, I'm going to be showing you how I add in the voltage regulator, which will effectively cancel out almost all ripple voltage. But just for this part of the circuit, you can see here that without the use of any filtering capacitor, we have this output, which is called a pulsating DC output, which is not ideal at all. However, on the right hand side you get something a little more closer to ideal, which is a rippled DC signal with a theoretical ripple voltage of about 3.2 volts from what I last calculated. with these values that I had discussed earlier. And I obtained that theoretical ripple voltage from this formula here, which states that if you just take 1/2 multiplied by the peak value of the step-down input voltage, subtracted by 2 times the diode turn-on voltage, because there's always going to be 2 diodes on whenever you're using the rectifying portion of the circuit, divided by the load resistance, multiplied by capacitance, multiplied by input frequency, and you get the theoretical ripple voltage, which, as I said earlier, was 3.2 volts. However, all sorts of unexpected problems come up in practice. Firstly, I thought it would be a great idea to use LEDs for my diodes to rectify the line voltage so that I can see the diodes turn on as a visual feedback that my circuit is working. However, those of you watching who have used LEDs before, or honestly anyone watching this who has actually read an LED datasheet in detail, will notice that the most voltage an LED can withstand before it breaks is no more than 15 volts for specifically a red LED. Not to mention, the max voltage reported in my oscilloscope, also known as Vmax, is 28.8 volts after the transformer, which is well above the red LED's max voltage. So as you can expect, I heard a loud clicking noise the moment I connected my signal to the circuit. Moving forward, I had to order 1N4007 diodes, also known as rectifying diodes, which can fortunately withstand up to 1000 volts across before failure. And 2 weeks later, the diodes arrived from literally China, and I was finally able to start making the circuit again. Unfortunately, I ran into another problem. So I didn't know where to ground the circuit. And I kept searching around the internet and saw different grounding locations in the circuit for a full wave rectifying circuit. However, I kept getting an incorrect output. And how I knew I kept getting an incorrect output was I essentially got the same output here on the right, but the frequency that I was observing was not 120 Hz and was instead 60 Hz. So what I did instead was I decided to try grounding different nodes in my circuit because I got impatient, and eventually it led to a short circuit, a burned resistor, and a broken rectifying diode. So, whoops, right? My last resort was to email my electronic circuits professor, Dr. Barad Bahraini, for help on where to ground my circuit. So, Dr. Barad, if you're watching this, thank you so much for your help. And he suggested to use the bottom of my load as the ground for my circuit here. So I'm not sure why I didn't think of that earlier, because it makes sense, and it ultimately worked. And so, of course, this photo here is the correct configuration. And like I said earlier, how I can tell that this worked was because when I tested the output without the filtering capacitor, I observed an output frequency of twice that of my input. And it makes sense because when the 4 diodes are doing their job, the negative cycle of the input sine wave should show up as the positive cycle across the load, meaning in the same period you'll have 2 positive half cycles, which obviously twice the input frequency. And again, like I showed you earlier, adding the filtering capacitor gives this output, which I observed a DC output of about 25 volts, and compared to a theoretical DC voltage calculation of 24.97 volts, if I did it correctly, which is very close to observation. At the time of this video, I had also just finished taking a course on signals and systems, so I decided to seek consultation on how to theoretically derive the output rippled signal from my signals and systems professor, Dr. Faranak Farzan. So Dr. Farzan was very kind enough to assist me with deriving the Fourier series representation of the output signal, and more specifically, she assisted me with deriving the transfer function, which I struggled to derive because it's a topic I'll study in further detail in my upcoming feedback control systems course. And what I have presented to you here is just my handwritten derivation of me finding the coefficient d sub n. And once I had found the coefficient d sub n, determining the transfer function, and then ultimately putting together the output signal, which I don't have plotted to you here at the moment because I ran into some issues with Desmos. However, the output is derived here. In theory, how the voltage regulator portion of the circuit works is simple. You give it a crappy DC signal that has some ripple to it, and the voltage regulator works its magic with its ripple reduction effect. Essentially, the voltage regulator smooths out the ripple to where it's negligible. Of course, the magic of the regulator lies in the IC, which is composed with multiple operational amplifiers, but it's a whole other story to get into. And for the purpose of the video, it's an electronic component that removes the ripple on a crappy DC signal. My creative take on this portion of the circuit was to use a variable regulator, like I said, and to vary the DC output depending on my choice of resistors. But to make it even more fun, I decided to use a variable 100 kilo ohm potentiometer for R2 in the circuit here, so that in theory I could create a variable DC output. In other words, possibly a variable DC power supply. So in order to determine the DC output range of my circuit, I had to go to the datasheet for the voltage regulator. So the datasheet of the voltage regulator states that the output voltage is given by this formula. If I first fix R1 to be 10 kilo ohms and use a 100 kilo ohm potentiometer, I can determine the output range of the circuit by first inputting the maximum value of the potentiometer, which is 100 kilo ohms, and upon using the maximum value, I get the maximum output voltage, which is 18.75 volts. In order to determine the minimum value of the DC output, I just simply punch in R2 equal to 0, and I get 1.25 volts. So therefore, the output DC range for my circuit is 1.25 volts minimum to a maximum value of 18.75 volts. After all is said and done, this is the complete configuration of the entire circuit, incorporating both the rectifying portion and the regulator portion. So as you can see in the regulator portion, this is the 100 kilo ohm potentiometer, and also what I forgot to mention earlier, this is a 6.8 microfarad capacitor, so yes, the same as from the rectifying portion. However, this capacitor is used to reduce the transient effect that comes from using the variable regulator here. And this is my oscilloscope probe. So after following my circuit schematic, I successfully arrived at a DC output. So specifically a variable DC output. And what you see right now is me playing around with the potentiometer, which in turn plays around with the DC output. And if you look carefully on the oscilloscope, you can see the DC output changing. Thank you all so much for watching. I want to again specifically thank Dr. Barad Bahraini for your consultation for this project and being so kind to supply me with the transformer, the regulator, and probably a bunch of other electronics I'm forgetting to name. And of course, I want to thank you, Dr. Farzan, for helping me with the theoretical ripple analysis, and more videos to come on my electrical projects.